In this video, we will see the problem maximum path quality of a graph, and what it means is we are given an indirected graph and then we need to calculate the maximum quality of a particular path. So we are given the input as edges where u is connected to v and the edge is the time, right? And what we need to do is if we start at node 0 and end at node 0, we have to take at most maximum time to complete, and whatever the value is, that would be the quality. That is what we need to return. We have to return the maximum quality of the valid path. Okay, so if you look at the example, if you see 0 1 2 and 0 1 and 3, we can go from 0 to 1, 1 to 2, 2 to 1, 1 to 0, right? So that would be a valid path because we are starting from node 0 ending on node 0. But if we go from 10 0 to 1, the time is 10, 1 to 2, time is 15, that is 25. The maximum time that is given to us is 49. So if we come back from 2 to 1 and 1 to 0 back, it's going to be 50. So we don't have that much time to do it. So we cannot go to this path even if the path is valid. It is valid only if it is done in the maximum time that is given. Okay, but then there is another way. The answer is 0 to 1, then 1 to 0, 0 to 3, and 3 to 0. Everything happens under 49, right? So that happens because 0 to 1 is 10, 1 to 0 is 10 again, that's 20, 0 to 3 is 20, 10, and then 3 to 0 is again 10. That would be 40, which is less than 49. We have found a path, and the answer that we actually need to return is the value of the nodes. That would be 43 plus 0 plus 32, and that is 75. So we do not, if we visit it multiple times, we calculate it only once. Okay, so is there any other part? No. So that's the final answer, which is 75. Okay, looking at the third example, the second example is a bit easy. Looking at the third example, we can see we can go from 0 to 1, 1 to 2, that would be 10 plus 11. Coming back would be plus 11 plus 10, which is less than 50, right? That would be 10 plus 11, 21, that would be 42, right? So is 42 less than 50? It is. So we have a valid path. It is within the maximum time given. So the answer would be 3 plus 2 plus 1. That's 6. But is there any other path which can give us better quality? So there is. It is from 0 to 1, 3, 1, 0. So 0 to 1, 1 to 3, and then back again. That would give us uh, 10 plus 13. That would be 46, and by 46, which is less than 50, and now the quality is higher. It's 4 plus 2 plus 1, which is 7. That is why we written 7. So 7 is the answer, right? So to approach this problem, if you already know now this is a graph problem. We have to go through a path. So if you have to go through a path, I think the best way would be to do a DFS or a BFS. We will do DFS. So DFS would be the solution where we go from one node to another, and come back to that node, and whatever values we have stored till then is the answer if it is the maximum. Okay, so in this case we go from 0 1 2 to 1 0, we find one value which is 6, and then we go from 0 1 3 3 1 0, we find another value 7, we return whatever the maximum is, that is 7, right? So we are given input as edges. So edge, edge, and edge, the connectivity is 0 to 1, 1 to 2, and 0 to 3. Okay, and these are the values of the nodes. And we'll take this example to go through the code. So we have these edges. So now we are given edges, we can construct a graph. So let's create an undirected graph, which we can do using default dict in Python. And when we create a graph, it will look something like this, right? So we have one node, it is connected to another node that is 1, and the edge is 10. In this case, that is the time. So from 0 I can go to 1 with time 10. From 1 I can come back to 0 with time 10. From 1 I can go to 2 with time 11, and from 1 I can go to 3 with time 13. That's what this means, right? So if you think about it now, if you look at the graph, I think when we think about DFS, we start with one node. So we start with 0, we check its neighbors. These are the neighbors, 1 and 0. And now since it's a depth first search, we look at the next one from 1, right? So we are going deeper. So from 0 to 1, we found this. So from 1, do we have more neighbors? Yes, we do have more neighbors, right? So we have these many neighbors. So should I go back to 0 again? that is a possible path. We can go to 2 as well, and we can go to 3 as well. So we explore all these paths through 1, and once we go to 0, we also see what happens. We come back over here, so we calculate the path again, stuff like that. But then we have to have a break condition, which is if we return back to the same node, we calculate the quality, right? Because that is the definition of a valid path. It starts at 0, ends at 0, so we calculate the path at that time. Okay, so from 1, when it goes to 2, from 2 it can also go to 3 and calculate the path. But if it goes to 3, I think our time is going to get over, so it never explores this path. It will just return back from 2, right? So eventually when we do all of this, we get this particular path, which is 0 1 3 3 1 0 and 0 1 2 2 1 0. Okay, so that's the whole solution. It's depth first search. We can try building it. So the first thing is, so our step 1 is build the graph. Step 1 is build the graph. How can we do this? So I've already done that. So we have graph equal to default tick, and this is going to be list, right? Now what do we do? So we iterate over the edges, because the edges is going to give you the nodes, and we store the time with the value as 1 comma 10 for node 0, right? So it would be, it's undirected, so we do both ways, right? So for u comma v, that's what it's given, right? So let's follow the same, right? uv, let's do that for u comma v in, and time as well, right? Sorry. So in graph, in edges actually, right? And now it's a dictionary, so it will be graph of u is appended to a tuple of v comma time, right? So u, we take 0 1 10, so that's u, it goes to v comma time, which is 1 comma 10 as a tuple. Okay, now we go the other way around. So graph of v, taking 1, it's an undirected graph, dot append, that would be u comma time, right, in a tuple. So that's it. That's how we create a graph. Now we have created a graph. Now do step 2 is just going to be DFS, right? Step 2, DFS. So we create a function DFS. What do we pass inside this? So we go from one node to another, so we need a node, right? And what else do we need? We also need values, because these are the values we will be calculating. So values, let's keep it val. Whatever value we take of that node. And what else do we need? We need the time, because that's the time we are going to check whether we are going above it or not, right? So time. So we have these 3 nodes. So what would be the base condition that we need? So if we reach back to the starting node, so if our node is back to 0, we return what? The quality. I'll define this. So we return the quality. We return the max quality, right? So we return the maximum quality that we have found. Since if we find 2, in this case how we find 2 qualities, we return whatever the maximum is, right? So we'll return that, we calculate that. But then we have started with 0, right? So 0. Now what we do, we go through all the neighbors. We have to go through all the neighbors, right? That is going to be for neighbor, and for neighbors that we find with the time, right? So we get the neighbor and the time. Let's do this current time. How do we find this? From the graph of the node, right? So node, from the node. So whatever node we passed, we are iterating the values of this. Okay, so that's the node. Now what? The next step is we have to check whether we have time to look at it or not. It could be that from the first node itself we can't do anything, right? So what we check is we check the current time plus the time that we passed through the function, if this should be less than or equal to the max time, right? And if it is, then we can go ahead, right? But now we need to also create something called as visited. Let's create it like this of 0 times length of values, right? So these are the nodes how many times we visited. So in this case it would be 40000, right? So what we do is we'll calculate the time and we check whether we have visited that or not, right? So even if we have visited, we can visit multiple times, so they do mention that. So I think it is mentioned here between, yeah, same node multiple times, right? So what we can do is we add it. So visited of neighbor plus equal to 1, right? But we don't do this here. What we do is we put this here, right? We right now we're just calculating the max time. It's less, so that's good. So it will be inside actually. So it goes inside. But then what else do we have to check? We need to add the values as well, right? So the value of that node. So we need to add a new value, that we have found. Ideally, it could be 0. So if the va- if you have never visited this, if it is 0, it means we have never visited this. So when we create this, we put the first element as 1 because that's how we start. But if we've never visited this, it's a brand new node, then what we can do is we just add that value, right? We add that value to new value. So we have new value plus equal to values of that neighbor, right? So we have more time. So we go inside, we just check whether we have already visited this or not. If not, if you have never visited this, then we can add the value, right? Because we don't want, so in this case, if you go from 0 to 1 to 0 again, we don't want to add 0 twice, or we don't want to add multiple times 3. Like in this case, in the third scenario, if you see 0 to 1, 1 is here twice, right? So 2 would be added twice. So it will be 3 plus 2 plus 2 plus 1, which is wrong, right? We just had to add the value only once. So if it is 0, that time only we add. If not, we don't do anything, right? We don't add that value. But then we mark it as visited. So, right. So once we mark that visited, what next? The next thing would be, that's it. Now we just call the DFS function. What do we pass? We pass the neighbor. So we are passing. So we took 1 and calculate everything. Now we pass to the DFS the node which is 1 here, and we check the neighbors of these neighbors, right? So this particular would have now neighbor of 1, so it would be 0, 2 and 3, right? So neighbor, DFS of neighbor, and then we need the new time, right? That would be current time plus time we saw, and then value would be the new value, right? So which we added right now. So new val plus val, right? Now if you see, we need to, if you have added something, we would be coming back. So if you go to 0 to 1 to 2, and when we come back to 1, we need to remove that we have visited to 2, right? Since we can do it multiple times, so we have to remove it as well. So we do visited of that neighbor, whichever neighbor we visited, we remove it as well. So that's how the backtracking would work. Okay, so we find something new, then only we add the value, which is the actual response that we need to return, and we mark it as visited. We add the multiple times we are visiting, right? And if you come back, if you backtrack, then we'll remove it as well, right? And okay, so that's done. But now we have not never calculated the maximum quality. So quality would be this, right? This is the value that we are returning, quality. So it just would be a maximum of the value. It would be val, right? We return that. Or let's do one thing. Instead of returning, we assign this to maximum quality. Now whatever the value is, it's always here, and this is the part we need to return, max quality. But we have not started the DFS yet. So how do we start the DFS? the DFS would start with 0 comma 0, zeroth node, and time is 0 at the start, but the value of that zeroth node, in this case it is 1, right? So it would be values of 0, right? But then we also have a visited. So just before this, we keep visited of the 0th element as 1. We start that, right, we put everything as 0, but before we start we make it as 1 because we are already visiting the 0th node, and then we start, right? And I think that's it. So maximum quality, we found the maximum quality. Let me define that. 0. So let's run this. Invalid syntax. This is wrong. Just run it again. Oh, so we could do self dot quality. Let's do a simple one. So let's do non-local max quality. Since it's a DFS recursion, let's do non-local max quality, and I think that should do it. Or you could just have, self dot quality is 0, so it's retained, right? Also, that got accepted, and I submit this. Right, so it passes all the test cases, and that is the solution.